I have a circuit, which is exactly what I showed you, the circuit with a current mirror, and we are going to plot the all the parameters from the asymptotic gain model. Which is the asymptotic gain? Well, the gain is minus 6 dB, as you should know. 450 millivolt per meter input would give 225 millivolt output. And this is like in this, if you take the ratio of the two, it's like minus 6 dB. And the black one is the loop gain. And you see the loop gain stops at about 1 gigahertz. So it appears that the bandwidth is large enough. The loop gain pulse product, it appears to me like a second order system, two dominant poles, because I see I see a slope here like a two dominant poles. And you see there's a little bit overshoot, the servo function, and the gain, of course, have the same shape there where the loop gain passes the 0 dB, and at the end, the gain approaches the direct transfer, which is the green line, the direct transfer from source to load. So the reference variable is chosen in a meaningful way because the asymptotic gain is frequency independent and minus 6 dB. That is what the ideal gain should be. So the ideal gain is equal to the asymptotic gain. Let's go to the HTML output because that is a little bit better in showing to you. Dual stage. Circuit data. So here is the schematic. That is exactly what I've shown you on the sheet, the netlist, and then you find here all inversion coefficients and stuff and the small signal parameters, etc. That is, I will go to that later if we need it, but at this point it is not important. So we just go to the pole zero analysis. And I did them for all types of gain. So we have gain, we have loop gain, we have the asymptotic gain, we have the servo function, and the direct transfer. The program cannot calculate the DC gain because there are too many zeros and poles in the origin. Although they cancel, maybe the way it is calculated cannot deal with it. There's a solution, and I will tell you later how to do so. The gain, you see, in fact, a little bit overshoot because the Q is not like Butterworth should be, 0.707. It's a little bit larger, so there is a little bit overshoot. The loop gain shows us indeed two poles, one at 0 frequency. That is easy to explain, I guess. The nice thing is you should be able to explain these poles. Yeah? So let's go to the circuit data. Here, this current source, F1, has infinite output impedance and is driving a capacitor. So that would cause a pole in the origin. And here we have 50 ohm, well, let's say 100 ohm, and the output impedance of the capacitor, of the transistor in parallel with capacitors, which gives us the second pole of the circuit. So two poles, and you can easily calculate those values and find that the other pole is at about 1 gigahertz. So we have seen the circuit has two dominant poles, and of course a capacitive attenuator at the input in the loop gain. We can select the controlled source F1 as loop gain reference, and then plot all the parameters of all the curves of the loop gain. What I also showed you that you can do the pole zero analysis for all the gain types. And so we have seen in the result that the quality factor is about 1 of the poles. It should be 0.7, and the loop gain has two dominant poles. And if you take the loop gain pulse product, of course, the DC gain cannot be calculated here because it's infinite, but the loop gain pulse product can be seen from the plot and can also be obtained from the expression for the loop gain, of course. So that is this this first stage, and let's now discuss the implementation of the current mirror. So as already discussed, the transistor should have a low transconductance for the noise. We are not going to verify with SliCap the noise of multiple stages cascaded. That is, you should realize that SliCap is a symbolic calculator, simulator, and it can make and generate extremely large expressions if you really want, but you cannot see anything from it anymore. So it should help you with the correct design strategy to do the most important analysis and help you with your most important design decisions. So, such as that the noise of the first stage should be dominant. And if we design as such, later when we are having a more complete design, we can add additional noise sources maybe, but it can be let's say the noise calculation can become very difficult because you have the transfer function, you need the transfer functions to all the nodes. Basically, the spectrum can usually always be plotted. There's no real limitation to that. But as soon as you want to calculate RMS values, you need to integrate. And symbolic integration of high order polynomials is not always possible. So that's why you should keep things simple.